in 2 minutes. Of course, we've listened to group one to five, and of course, it's gonna be the turn of group six to let me see. I think that's gonna group six to probably 10, 11 today. Okay, is group six ready?
Yes, can I share my screen?
Yeah, no, now.
Not
Just
now.
yeah. So okay, thank you for responding. Group six is ready. Is group seven ready? Two. Is group seven ready? I need group seven.
Yeah,
Who is
yeah.
okay, you're ready. Okay. Is group eight ready?
Yep, we're ready.
Okay, thank you so much. Is group nine ready?
Yep.
Is group nine ready? Group nine?
Yep. Yep. Yep.
Okay. Okay, then what about group 10? Is group 10 ready?
Yes, we are ready.
Okay, thank you so much. I think what about group 11? I think we have like five groups today, right? Or six to oh, okay, 6 to 10. Maybe. Yeah, 6 to 10. Okay, so group six, you can let me see. I'm gonna enable okay, group six can share, you can share your screen. Group six, you got the floor. You only have 5 minutes, and at times I may allow like additional maybe 1 or 2 minutes, but let's just see how it goes. Okay, so group six can share.
Okay. Can you see my screen?
Yeah, we can see your screen.
Okay. Okay, so I can start, right?
Yeah,
Okay.
start.
Okay. High-dimensional data sets are quite common when it comes to many areas of data analytics and machine learning. These can involve hundreds or thousands of predictor variables for relatively few observations, which resulting in an increase of computational cost, storage concerns, and a higher risk of overfitting in predictive models, which can lead to mediocre model performance. Oh, so sorry, I didn't do the okay. Um, One technique to avoid working with high-dimensional data is dimensional reduction. And what this does is that is reduces the features in a model but still maintain like most of the meaningful details. And the goal of this technique is to compress the original high dimensional data into a lower dimensional representation without losing all the crucial information. And by finding a new representation of our features, we can have a new model that are simpler to interpret and visualize. Okay. And classical MDS, also known as classical multidimensional scaling, is one of the methods of dimensional reduction. And MDS um aims to represent high dimensional data into a lower dimensional space by focusing on the pairwise similarities between data points. Um, it has a goal of preserving similarities between points as much as possible so that the relative relationship between data points is maintained in the reduced dimensional space. Um, the function to use this on RStudio is called CMD scale, and this function allows us to look at the goodness of fitness and measure the amount of variance captured by the dimensional reduction. And the background, okay. So using pairwise distance matrix from our oh, um okay, wait. Okay, I'm sorry. Using pairwise distance matrix from our data set, we would aim to find a new data set, but in a lower dimension where the pairwise distance of the new matrix would be very similar to the original matrix. And to do that, we would minimize the stress equation, also known as the least square distance between the lower dimensional and the higher dimensional distance matrices. And usually, when you get like low stress, it just means like it's a better fit model. And for our dataset experiment, we applied MDS to a subset of handwritten digit dataset, which contains 4,000 and 34 samples of digits of 0, 1, 5, and 7 to reduce computational complexity. We all predicted
You
that the
got
MD,
you got 2 minutes, two
right,
more minutes.
okay. We predicted MDS would review distant clusters for each digit with overlapping expected for visually similar digits like 1 and 7 because they're very similar to each other. Um, okay. For analysis, MDS achieves 28% goodness of fitness and 5% stress, indicating that moderate distortion and results in the results show clear digit clusters with some overlapping, confirming our prediction. And for data set number 2, the second data set we perform MDS on is a random sample of term document matrix derived from 2,225 news articles categorized into 5 topics. A sample of 2,000 terms was used to use due to computational limits, giving the high dimensionality and sparsity of the data. And we all expected that the MDS would not perform well in this representation of the data due to the curse of dimensionality. And for an analysis, um, the MDS results in long-term, the MDS results for term document matrix showed that it had a 2% goodness of fitness and a 91% stress, indicating poor representation of of the original distances. The analysis reviewed high distortion and no meaningful insights. We would need more dimensionals to have a meaningful representation of the data. So, in conclusion, MDS is very effective for preserving meaningful similarities while reducing high dimensional data when those similarities are significant. Um, okay, that's it. Any questions?
Okay, so can we give the presenter a round of applause? Okay, so before questioning, I think I'm actually seeing some students they not turn on their video, and like I said, I'm only gonna write I'm only gonna mark you present if you turn on your video. So I think I see about 6 students that are not turning on their video. That is very, very compulsory that while you are attending a presentation, you have to turn on your video. Okay, so if you don't turn your video, there's no way. I think I have about 7 students now. So please do turn on your video. I want to see who is behind the scene. Thank you. Okay, presenter, thank you again for a wonderful presentation. Before I make my suggestion, is there a question from the floor? Is there any question from the floor? Okay, so without any question, I think you've really done a great job, but the only thing that I'm actually gonna add, I believe you're working on dimensionality reduction with MDS, and of course, I will advise in your report, make sure you state clearly whether you are able to achieve the objective of projecting data point into from higher dimensional space to lower dimensional space. And also I will advise that you use more than one metric of evaluation. When you look at what we did in class, I think I actually presented more than one metric of evaluation. Okay, so I wanted to be able to take a decision using each of the metric of evaluation that we use in class. Okay, so aside that, I think you actually had a very good presentation, and thank you. Okay, so you can stop the sharing. Why group 7 can start sharing. So group 7 is your turn.
Yeah, hi. I'm sorry, let me pull it up.
Okay.
Okay, can you see that?
Yep.
Okay, perfect. Okay. Hi, I'm Cora. I'm presenting on behalf of Group 7. Our topic is Bayesian networks, and we implemented this on the Titanic dataset. Okay, so I'm first going to start off with like where did it come from? So the concept was created by Judio Pearl in 1985, and his kind of inspiration or goal for like why he created it was to create a model that could handle the complexities of real life, but still make efficient reasoning under that uncertainty. And then a little bit more specific to Bayesian networks, like what makes up a Bayesian network. It kind of falls under the umbrella term of probabilistic graphical models, and it represents a set of variables and conditional dependencies through a directed acyclic graph. And if you look at the graphic in the middle, it kind of shows what it looks like. So it's a bunch of independent variables with directed edges that show dependencies, so like how one variable affects the other if they're conditionally independent or not. So there's kind of two approaches to creating these models. The first one is constraint-based methods. So this is kind of using a statistical test, like a chi-squared test for conditional independence and determining how these variables are impacting each other. One disadvantage of this, though, is that it's kind of better for undirected graphs. So we chose to focus on the score-based methods. So this is kind of using different algorithms to measure how well networks fit the data. And this one is particularly great because there's so many different metrics you could use to score. So it leaves you with a lot of flexibility of like what model you want. So you're able to like interpret and choose your model based on what metric you choose. One disadvantage of this though is it does sometimes lead to overfitting, but I'll mention that again at the end in relation to our model. So this is our data set. It's made up of 4 categorical variables: class, sex, age, and survived. So class is just for second, third, or crew, sex, male or female, and then age, child or adult, and survived, yes or no. So a little bit of how we made our model. So we created 4 different structures under different criteria. We used BIC, AIC, FNML, and VDLA. We focused on hill climbing algorithms specifically. And then we plotted each Bayesian network, edited the final model, and then we looked into our data for further insight to support our model. So I just put like the R code for actually creating the models because it's a lot of R codes. I didn't want to include it all, but that's kind of how we created each model in R. And then these are our 4 models that were created. Each model kind of has its own advantages and disadvantages. BIC and AIC are kind of the most commonly used when creating Bayesian networks, so we kind of focused on that. Although BDLA is kind of really good for categorical variables, which would be our case, there's a chance that FNML and BDLA don't have that same level of practical support as BIC and AIC because they're more commonly used. And then deciding between BIC and AIC, we know BIC punishes complex models more, and we kind of have a simpler data set, so we wanted to go with the simpler model, as well as BIC just kind of made the most sense practically looking at the graph. So these are kind of the few criteria we looked at when we were deciding which model to use. So how
2 more minutes.
Okay, so how well does it fit? Like how complex it is, interpretability, predictive accuracy, just kind of practically does it make sense for our data set? One caveat to our model is we did choose BIC, but we made a small change because I'll show it again, but survived and age, it had age was dependent on survived, which didn't make a lot of sense to us practically. And the FNML and AIC both had that arrow switched. So we kind of saw support for switching that arrow to be survive impacted by age, which we know from knowing about the Titanic and what the data set is, that it really should be that survived is dependent on age. So we switched that arrow. So then this is our final model that we created. So survived is dependent on all three other variables, which makes a lot of sense if you know anything about the Titanic. And I'll show some support for that with some data in the next slide. And then we have class impacting all the other variables. So this is a little bit about our model. This is the equation for probability. There's 13 independent parameters. The probability of survived is 8, has 8 parameters. Class is 1. Sex and age both have 2 parameters. And as I said, here's a little bit of support for why we switched our model to be what it is. This is all the different variables and how they impact your percentage of survived. So if you look at this, if you're like a female in first class, you much more likely to survive than like a male in third class, because that's only 25% of third class as opposed to 62% of first class survived. Same with age, child versus adult, 52% of children survived and only 31% of adult. So that's kind of the further data insight that supported our choices. And then a little conclusion. So some limitations that we had is that this was a simple data set, only like 4 categorical variables. And as I said before, the score-based method is prone to overfitting. So there's a possibility of that. And the other limitation is the fact that we customized our final model. We didn't just use the EIC one, we switched the arrow for one of them based on like our own interpretation and what we thought made sense. And then overall, just impact of Bayesian networks. They're really great because they reduce parameters and provide a very simple visual for complex models and relationships. It's a lot easier to look at a Bayesian network than to read off a list like this variable is dependent on this variable, which is dependent on that one. It's a lot easier with this visual, which makes it really simple with the directed edges. And again, very helpful in predicting likelihood of events. And that's all we have. So any questions?
Okay, beautiful presentation. Can we give her a round of applause, please? Okay, then I'll do the time for question and answer. Is there anyone from the floor who want to ask a question? Is there anyone want to ask question? Okay, so I actually want to commend this work, and I love the idea that the variables in the Titanic were digitized, like categorized. I actually, because when you take a look at what has been done in statistical data science literature, you actually gonna see they've you know they use a different statistical or machine learning algorithm. So using Bayesian network, in this regard, I'm actually gonna say it's highly commendable. Okay, so my suggestion is just like, okay, you make sure your report is detailed about the choice of the selection criteria. I love the way you show all different kind of collection. I mean, selection criteria. When I talk about selection criteria, I'm actually referring to the choice of an appropriate graph. Okay, so the graphical structure. Okay, so make sure it is well detailed. Aside that, I think you guys have really done a very great job. So can we appreciate them once again? Yeah. Okay, so group 8 is your turn. The group 8, you can share your screen. Group 8.
All right. I will share my screen really quick.
Yeah.
There we go. Can you guys see it?
Yeah.
All right. So my name is Keenan. I'm presenting on behalf of Group 8, and we did Principal Component Analysis, or PCA. And so let's get right into it. So what is PCA? The goal of PCA is that it's a dimensionality reduction technique whose goal is to reduce the number of features in a data set while also maintaining as much important information as possible. And so it takes original variables and it transforms those into new uncorrelated variables called principal components, which are just linear combinations of the original variables. The first principal component captures the most variance in the data set, with the subsequent components capturing, less and less after it's ordered. And so here are the computational steps of PCA. So first, if you need to, you should scale the data. If it's all on the same scale, obviously you don't need to. And then compute the correlation matrix. If you don't scale the data, then you should do the covariance matrix. And you just have to make sure that that's centered. So, the mean is around 0. After that, you would compute the eigenvectors and eigenvalues of the chosen matrix, where the eigenvalues represent the amount of variance captured and the vectors represent the direction of the principal components, which is also very important. You order the PCs, and then you select the ones that capture the majority of the variance and project the data onto them. So what scenarios would you use PCA in? Really what they're good in is high dimensional data sets. So if you have a ton of variables and you want to reduce the number of dimensions in a high dimensional data set, then the complexity of model decreases when you do this, which reduces the likelihood of overfitting. Also, in the case where you want to produce visualizations of data, maybe you want to cluster it, or you just want to have a visualization to better interpret the data. Reducing dimensionality allows for these visualizations to be produced in 2 or 3 dimensions, which is much, much easier to interpret than, say, in 17. So our data set was the IRIS data set, and we did this in R. So we applied PCA to the IRIS data set to try and reduce the dimensionality of the data and create visualizations of the clusters. It only has 4 features, which is actually quite small for our use of PCA, but we found that PCA was very suitable for this data set because after scaling and removing, differences in variances between variables, the PCA, the principal components actually explained a lot of the variance in the data. And so moving on, this is our code. The first PC, as you can see in the bottom right, explains about 72% of the variance, total variance or variability. And then after you use the second principal component, it gets up to 96, which is very, very good in just 2 PCs. And we use PRComp in R to do this. And then here is a scree plot, which just helps us choose, how many dimensions we want to visualize the data in. And we chose 2 here, as obviously you can see that the biggest drop off happens between 2 and 3, but also because 2D, data is very easy to visualize compared to 3D, and it does explain 96% of the variance, which is a very high amount. Here's a scatter plot, and this is a really good visualization of something we'd apply clustering to. It's pretty easy to see the clusters that this could potentially have by species. And so this scatter plot, it makes it really easy to visualize the differences between these irises. And then the biplot, which is also really, really helpful because we can kind of see the relationships with the principal components here, right? We can see that even if you look at the pictures in the bottom left, Iris setosa has that very high amount of sepal width, and that's what separates it from the other 2 types of data or types of flower. And so it makes it, you can see the direction that sepal width points it in. It's very clearly, negatively correlated with both principal components in that direction. And you can see that the other 2 are very highly correlated in that first principal component direction, and obviously have larger petal length widths and sepal lengths because you can see kind of where those eigenvectors are pointed at. So this is a really, really easy visualization to try and understand our data, because you can literally look at the flower and understand everything you need to know about the flower by looking at the data, which is fantastic. That's why this data set is so good with principal component analysis. And so, in conclusion, this project shows the versatility and effectiveness of PCA in dimensionality reduction and visualization. It fits very well to the data set with 95% of the total variance of the IRIS data set, showing that it can reduce complexity but still have incredibly accurate outputs. And then we had those, plots to kind of show that and visualize that, which is the whole point of PCA. So are there any questions?
Okay, wonderful. Another wonderful presentation. Can we give the presenter a round of applause? Thank you so much. Okay, this is question time. Okay, so you need a question. Let me tell you, when you ask the presenter question, that we give the presenter opportunity to improve, this group to improve on their work. This is the reason why we go to conference. We go to conference because we actually want to be involved in constructive criticism, that will improve our work. So in case you want to ask question, you can go ahead.
I have a question.
Okay, go ahead.
So with the iris data set originally was it 4-dimensional or 3-dimensional?
Yeah, so originally it was 4 dimensions, right? So you can see
4-dimensional. And then
the 4 variables here. Yeah.
okay, and then you reduced it down to 2 dimensions.
2
And then
dimensions.
yeah.
Well, two primary components. Yeah.
Okay. So because would you say that because
Sorry, go ahead.
the original data is so low dimensional, that's the reason why there's 95% in the first 2 principal components? Or is that typical?
That's a good question. No, it's not typical for 95% of the data to be explained by the first 2 principal components. Usually there's a lot more, especially for high variable data sets. If I had to say, I would say yes, that's probably part of it. I would also say that if you can see, there's kind of 2 big clusters that you can see here. And they're both differently explained by the principal components, right? So like the first PC really highly explains versicolor and virginica, but then the second PC, it's negatively correlated with the first PC, and they kind of all move in the direction of the second PC. Some of them on that vertical axis, about half of them. So that's why the first one explains about 70% of the data, then the second one, comes in with that 25%. So that's why I would say it does that. Thank you.
Okay, gotcha. That makes sense.
Yeah, thank you so much for the question and the response. Of course, excellent response. Because let me tell you this, if you look at the, the techniques you'll be learning in this course, majority of our techniques actually, they are dimensionality reduction techniques. If you look at whether you're talking about PCA, you're talking about MDS, you're talking about ISOMAP, even when we're talking about Bayesian network, it's also a dimensionality reduction technique because we're focusing on dimensionality reduction technique because we live in a world where we are likely going to, experience a high dimensional issue. And that's why we need technique that can address that. So I'm gonna say Group 8, you've done a very great job. This is well explained, well presented. What I'm only going to say is that in your report, don't forget to put the equation. There's gonna be equation, the principal component that you choose, it's also gonna be a linear combination of even the original for feature. So I really want to see the linear equation. You get what I mean? So make sure that is incorporated in your report. So except that, I don't think I have any other suggestion to add. So you guys have done a great job. Okay, so you can stop the sharing. I'm gonna call on group 9. So group 9, if you're ready, you can share your screen.
Let me share my screen. And before we get started, I would like to apologize that we might run out of time, but I think there is still 25 minutes left. So I think that's fine, but I will say sorry for group 10 and other classmates. So hi folks, this is group 9, our topic is about matrix completion. And here's today's agenda. Let's get started with our data set. Our data set is about environmental features from the ERE5 platform from the European Commission. And our data was collected daily without missing values. So we use a Python script to drop some observations as our missing values. That's why we can compare the accuracy of each algorithm with the original data set via cosine dissimilarity and RMSE. So we choose both unsupervised learning method and supervised learning method. And let's get started with unsupervised learning. So the intuition behind the unsupervised learning method is to discover the hidden patterns or structures in the dataset. We use SVD and ALS here. Okay, the general idea for the unsupervised learning is first we initialize our matrix by filling missing values with some initial values, and then decompose the original matrix to get the low rank approximation, and then we reconstruct the matrix and fill in the missing values. Finally, we repeat the step 2 to 4 until convergence. And here is the pseudocode from our lecture notes. And we use two approaches here. The first one is SVD. We use the decomposition x equals u times sigma times v transpose. And we have a manual iteration process. We use an infinite while loop until convergence. And we also use a R function of input with argument type equals SVD. And here is the code of our manual iteration process based on the lecture notes. And the second approach is ALS. The decomposition here is x equals u times v transpose, where u is for the row features and v is for the column features. For ALS, we only use the R functions of input with argument type equals ALS. So we are all talking about unsupervised learning, but if you remember, there is one sentence in our lecture notes: matrix completion can be seen as both an unsupervised or a supervised problem. So what will happen if we use some supervised learning method? So the intuition behind the supervised learning method is to consider matrix completion as a prediction task. We have the input of our known information and we have the output of missing values. The algorithms will learn to map patterns in the feature to observe values during the training process and then apply this knowledge to predict missing values in the test process. And especially we use deep learning here for some algorithms like RNN, GNN, or transformer. They will capture the complex or nonlinear relationships between the features. Our approach here is GAN, Generative Adversarial Network. For a GAN, we have two parts. One is a generator. It will generate the missing values as real as possible. And we also have a discriminator, which will find the values generated by the generator. After training for many epochs, we will get a stronger generator, which can generate almost the real values that the discriminator cannot detect anymore. And we will finish our training with the generator and the discriminator reach a Nash equilibrium or reach the max epochs. So what impresses us most is the GN result. We choose the feature longitude from the 10% randomly dropped dataset. And if you can see the first few missing values, GN predict exactly the same number as the original dataset. And here is our evaluation. First, we evaluate the outcome via cosine dissimilarity, which will measure the similarity between two matrices. And we also use the evaluation via RMSE, which will measure the difference between the field entries and the original entries. And based on our evaluation, our conclusion here, all supervised learning methods perform similarly for the same dataset. And unsupervised learning methods tend to feel similar but inaccurate values, which means the result has lower cosine dissimilarity but higher RMSE. But on the contrary, for supervised learning method, it tends to feel accurate but dissimilar values, even values in the opposite direction, which means the result have lower RMSE but higher cosine dissimilarity. And the supervised learning method is sensitive to the structure of known information. It performs better for the drop by fixed step or dense information. And finally, supervised learning methods perform relatively worse when increasing the number of missing values compared to the supervised learning methods due to the insufficient information to train. And our limitations: first, our two unsupervised learning methods have difficulty dealing with rows with too many missing values. We have for our 50% randomly dropped dataset, there are a few rows with all missing values, and our algorithms cannot deal with that. Also, SVD and ALS ignore the unit for different values, which means we need to standardize our datasets first, complete the matrix, and do the inverse standardization to get our final dataset. And for the supervised learning methods, neural networks incur huge amount of computation expenses. And because of the high computation expenses, our neural networks are actually not fully trained. And the performance of our neural networks vary dramatically for positive and negative columns because we use value for generator and sigmoid for discriminator as their activation functions, and their codomains of these two functions are not negative. So that's why our model cannot predict negative values. So this is all for today's presentation, and we already posted our codes on GitHub, open source via MIT license. And if you want to see that code, you can come to that website and download our code. And any questions?
Okay, so wonderful presentation. Can we give the presenter a round of applause? Okay, so before I make my suggestion, is there any question from the floor? Is there any question? Okay, so actually I allowed you know, the presenter to go beyond 5 minutes because I think he actually you know, gave us that information before he started that it was likely, and we also spoke about it because the approach that is trying to compare, we haven't done one, you know, of course, you know, most of our techniques in this class have been unsupervised learning. And of course, I also encourage, of course, you know, if there is something we haven't done that is performing greatly, of course, that can also be brought in. So, my question is, I need you to go back to, can you go back to where you actually, you know, where you have the original matrix and where you have the missing one, and you mentioned that how many of the missing one were computed exactly? Because I had you mentioning exactly.
I think we have like about 800 rows, and for the 10% randomly dropped data set, for each row there are about 80 missing values, and the same as like the 20%, the 50%.
Okay, because my worry is this: if the results exactly match the original, what you are trying to tell us is that the root mean square error supposed to be 0 for that. Like there's no distance because the root mean square error is more or less like a distance. So are you saying it is not all missing values that are predicted exactly according to your model? Not all, right?
Yeah, not all. Like if you can see here, like our result is 139, and the original is 116. So these two numbers are not the same. So
Okay.
only for this two entries here.
Okay, that really makes sense. Because when you talk about algorithm, whether statistical technique or models does not give exact characterization of reality. Okay, so that really makes sense. So once again, can we give this group another round of applause? Yeah, good job. Good job. So, what I'm gonna say, what I want you to, my suggestion is that when you are comparing supervised with unsupervised technique, I need you to search the literature. Um, you know, the metric of evaluations, um, you know, have to be compatible. What I mean by that is you have to make sure that the metric of evaluation you're going to use should be the one that can be used when we are comparing both supervised and unsupervised learning. You get what I mean? So make sure we just want to be on. I know for on unsupervised learning, we got some metric of evaluation. For supervised, we got some metric of evaluation. But when you're now comparing between supervised and unsupervised technique, I will advise that you check the literature and incorporate that in your report. So once again, wonderful presentation. Okay, is group 10 ready?
Yes.
Okay, group 10, you got the floor. You know, you can share your screen now. And that's gonna be the last group of the day. Yeah, 2, 3, 4. Yeah, group 10.
Okay, we are group 10 and we're presenting on Bayesian networks, specifically when there's missing data. So an overview, I'll talk about the objective, the methods, the results, and then the conclusion. A little introduction on Bayesian networks. Bayesian networks show conditional relationships between parent and child nodes. This can be used to derive probabilities and dependency of the events involved. The accurate construction of these networks is very important and can be impeded by missing data. And depending on how the data is missing, we can use different algorithms to find a better network. The data that we looked at was the 2021 Consumption Activities Mail Survey. This is real-world data from University of Michigan that they published. It involves roughly 4,000 individuals and 255 questions. We reduced this down to 10 just for easier computing and visualization. It also has missing data, roughly 3,000 NA values, and roughly half of the individuals have at least one NA in their row. The data also is mixed structure, so it might be fill in the blank, multiple choice, true or false. And so we wanted to make it all a 0 or 1, true or false. And so we made anything that was complex into a 1 or a 0 based on if it was in the upper quartile. So something like how often your body is used in work, that might be an open-ended question. We converted it to a true or false for someone that often uses their body for work. So we use structural expectation maximization. This does multiple rounds of learning the structure and then imputing the missing data and then making a new structure and comparing the old to the new structure. Specifically, it compares BIC scores and it determines if it converges, then it will stop. So it learns the structure over time as well as filling in the missing data. So this is an example of bad networks. This is simple hill climbing applied to the data without addressing the NAs. On the left is where we just left the NAs in. You can see it's way too complex. And then on the right is when we removed roughly half of the rows, all of them that had NAs. You can see it's much more simple, but we can worry that it might be too simple because we just lost a bunch of information, and it also might be biased depending on how the missing data is spread out. So this is the result of SEM. It took 349 repetitions to make the structure. And you can see it's kind of in between the two bad structures, which is expected. It contains more information than if we dropped all the NA rows, but it's also less complex than if we just left all the NAs in and that muddied it up. So we also evaluated this. We did this with bootstrapping. It was 1,000 simulations where each is a resampling of 1,000 individuals from the original data. And then we compared performance metrics from this bootstrapping, and we also looked at graphical lasso. So first, within the bootstrapping, we were able to find the frequency of each edge appearing. This is sometimes referred to the edge strength. You can see that this varied quite a bit. There are some edges that are only 3% frequent and others that are 92%. So different edges or different relationships have different strengths involved. And then from that, we can also look at metrics. Sensitivity was a bit low, so there's this ability to find true edges. Its specificity, though, so its ability to not find false or to only include true edges was quite high. So in that SEM model, we can be confident that all the edges are true, all the edges that it found are true, since it has high specificity, although there might be more edges that it wasn't able to find because the sensitivity was quite low. In general, we're actually okay with this because, as you saw, a lot of those edges were quite weak. And so if it found any more edges, they're likely going to be weak as well, which we don't always need since we do want a simple interpretable model. And so because we had that varying strengths of edges, we also wanted to compare it to graphical lasso because graphical lasso is able to enforce sparsity. So we used tenfold cross-validation to find a lambda value of 0.1, and that formed the final network seen on the right. Despite enforcing sparsity, it was still more complicated. You can see some of it are cyclic networks. And so overall, we found that this model was a worse representation of the data compared to our SEM data. This also did not address the NA values, so that likely made the model worse. And then because we had those different edges, we decided to clean up the network by removing some of the weaker edges and only include the strongest edges to maximize the interpretability while retaining as much of the relationship information as we could. So then we can clean this up and insert the titles in. And this is our final network. You can see that we started with, or if we had no model, it'd be 1,023 parameters. But with our model, we are down to 17. It's a very interpretable model where we can see the dependency between the different true or false variables. Something I found most interesting was that the probability that someone was happy with their current finances was independent of the other 9 variables that we examined. And then other things could be checked too. And then finally, some conclusions and potential improvements. Because the data was very mixed, some of it was, normally distributed, some of it was true or false, some of it was, A, B, C, D. We had to convert it all into the same form, but how we did that, we just used the upper quartile that may have imparted some biases and lost a lot of information. So how we decided to do that, we could change. We could also use more data. This is a yearly published survey, and so we could have combined multiple years together to find more patterns. And also, we only used 10 out of 255 available variables. We could have used all of them and then tried to cut it down. And then finally, we could try to search literature for expert knowledge to try to confirm different edges that are present in our network. Thank you. Questions?
Okay, can we give the presenter, can we appreciate him for excellent presentation? Okay, this is time for question and answer. Any question from the floor? Okay, I'm actually, before I give my general remark, I want to commend this group for doing a very great job. Trying to use the idea of a Bayesian network to input missing values. I'm gonna say this. Our technique in statistics and machine learning, they're doing very great job. Imagine you're talking about missing values and you want to benefit from the idea of a Bayesian network. The question I'm going to ask is this. Um, I know that when, let's say categorical variables, maybe some values are missing within categorical variables, I know they normally assign, the value with the highest probability. And of course, for continuous variable, okay, the way we infer from the, after constructing the graph, you learn from the parameter you want to infer the missing value. So for continuous variable, we use the expected value, which is the mean of the posterior distribution. Is that different from, I need you to tell us, how do you handle categorical missing values? How do you handle the continuous missing values? I really just want to know whether your approach is different from the conventional.
Yeah. So before we did a lot of the analysis, we converted everything into just a Boolean true or false. And so the final data imputation was also in that Boolean true or false. And so we weren't able to deconvert the values from Boolean back to the original structure. And that was definitely a limitation of this. If we kept it in a more complex structure, such as different factors instead of Boolean, we might have been able to keep more of that information.
Okay. Thank you. Thanks for that. So, what you need to do, you try to consider my suggestion, trying to, by the time you write in your report, trying to specify whether the method, the approach you use, how is different from, if it is the same as the way we input categorical missing variable, I said assigning value with the highest probability, and if it's also the same with the way we input values in the continuous random variable where we make use of the expected value, which is the mean of the posterior distribution. So if it is that approach or not, make sure it is well stated. Aside that, I'm going to give a general comment. I think today we have 5 groups, and of course, this is gonna be group number 5 for the day. Now, let me say this. I want to pass a general remark. I have a lot of confidence in this class, and all I can authoritatively tell you that all your presentation from group 1 to group 10, okay, if they are fine-tuned, they can actually be submitted to the top journal. Okay. I don't know whether you are thinking in that direction. You all have capability of a ability to go for graduate study, from what I'm seeing here, uh, you've really done a very great job. Okay. I can tell you that, if you put all of this, if you submit for consideration in top journal body, your article is going to be accepted. I can boastfully say that because you put a lot of energy, you put a lot of commitment, a lot of dedication into this because it's not easy, you know, uh, working with something, presenting it the way you've done. So it's not easy at all. A lot of things go behind the scene, and I actually need to commend your effort for that. All the presentation today, of course, I'm really super excited. Okay, so I actually sent a message yesterday. You can check the announcement section about the deadline for submission of the final report. Okay, so you can check. So you can just try it and fine-tune the work with the suggestion that I've made. But aside that, you've done a great job. You've done a great job. So Friday is another day. I decided not to post any assignments this week because I wanted you to fully concentrate on this presentation. Of course, this is an assignment. So the presentation is an assignment. It has a huge weight, but I wanted to succeed. So I think I'm highly satisfied with your presentation so far. Is there any question for me at this time? Is there any question?
I have one question for the final exam. So will you post some sample questions for the final exam or just
Yeah,
the study guide?
I'll definitely do that. I don't want to post now. I want my postings to be after Friday because I know that would distract students from. I wanted you to have a wonderful presentation because what we're doing this week is an exam. You know that? It has a huge weight too. So that's why I don't want to distract you from that. So that will be posted. That will be posted after Friday. Of course, next week it's going to be a revision week. And of course, I'm also going to talk about one topic, just in one class. And after that, then we'll go over the areas that will be covered in the finance. So yes, it will be posted after this Friday.
Okay, that makes sense. Thank you so much.
You're welcome. I also want to answer to a chat. I think a chat came in. Somebody said, let me see. Are we taking final exam in our regular classroom? That's a very good question. I notice the regular classroom is kind of compact. I've sent a message to the Office of Class Management. And of course, if there's going to be any change, okay, to the venue, you're going to hear from me through the announcement section. And of course, I want to believe before Friday, I'm actually going to get the response from the Office of Class Management because I noticed when you were writing the midterm two, midterm one, it's kind of compact. I wanted a spacious classroom for the final. So information about that, of course, I believe by Friday, we should know about it. Is there any other question before we go? Any question, any other question?
Yes, I have a question that do we have in-person class next week?
Okay, that's a very good question. If Let me just say, up to this moment, there's still gonna be in-person class. But if something change, of course, I will inform you ahead of time. If something change, I'm gonna. Okay. I let me say this because I know some students. They're gonna start their final in other courses. Do majority of you support that we should have remote maybe revision, whatever class we're going to be having now, should we be doing that on Zoom? Do you all agree to that instead of coming to class? Okay, do you know what you're going to do? You're going to send me your response immediately after this meeting. Okay, if it is yes, if you say yes, it means we should be having remote class. If you say no, if I see one no, then it's gonna be in person except something happen. So you may not you may not say your response now. Send your response through the email, through my email. When you say yes, then it's gonna be remote. Okay, we're gonna meet remotely. Okay, then when you say yes, we meet it remotely. But you know what? The final exam is in person exam. Okay. Somebody said, are we still going to have? Oh my God. Somebody said, are we still going to have a party? From what I'm seeing so far, we are likely going to have the party. So the party is likely going to come after you see your final results. I know from what I'm seeing so far, this class has been excellent. Okay. I can, this class can compete favorably with any college in the United States and any college in the world. I can tell you when it comes to statistical machine learning. I know what I'm talking about. Whether you want to talk about Harvard, you want to talk about MIT, you want to talk about University of Oxford, when it comes to statistical machine learning, this particular class can actually compete favorably. I have 100% confidence in what I'm saying. Okay, so keep doing what you know how to do better. Okay, don't ever rule out yourself in anything. Believe you can actually succeed excellently. Don't rule yourself out. And if there's anyone who gets stuck, make sure you always reach out. Okay, for the person that has a question about the party, thank you for reminding me. Okay, we're still gonna have it because you guys are doing well. Okay, in the absence of that question, like I said, we're gonna meet again on Friday for the last phase of the presentation. Is gonna be with 11, group 12, group 13, and group 14. I believe we're also gonna listen to wonderful presentation from those groups too. Okay, 10 so far, 4 more to go. Okay, we're meeting on Friday, but you know what? Immediately you log out today, send me a message. Send yes. The moment you say yes, it means our outstanding classes is going to be conducted remotely. But if I see one no, no, now, not now. Some people have said it through the chat. I want it to send through my email. Send through my email. Okay. Okay. Make sure you all stay safe and have a lovely day. Bye for now, everyone. See you on Friday. Yeah.
Professor, I have a quick question. It's
Oh, go ahead.
individual.
Yeah, go ahead. Go ahead.
I had talked to you about moving my final from the 18th to a different day because I'm out of town. I was wondering what the status was on that.
Okay. Yeah. I think I was planning to reply to your message today. If students have a very genuine reason, it's something that can actually be done. So I'm gonna reply to your message and I'm gonna tell you what is visible. Okay. I will do that today, so watch out for my reply.
Okay, cool. Thank you.
You're welcome. Okay, so bye for now, everyone.